All right, so we have section 8.3. Please put this in your notes quietly. Section 8.3, rational functions and their graphs. So we're talking about graphing these rational functions. And what I would like you to have down is our first term, rational function, and put an example of it is f of x equals p of x over q of x, where p and q are polynomials. And then I'd like you to get these three equations and these three sketches into your notes, please. All right, so we have three examples of rational expressions here. And what we're going to start talking about are the ideas based on continuity of graphs. So if you had to look at these three graphs, and I wanted to know which of these three graphs you would think is a continuous graph, even without me telling you what that means, which one would you think is continuous? Patrick?
The one in the middle.
The one in the middle? Not.
One.
The first one? Why would you think that one is?
Does it stop?
Yeah. So if you were to take a pencil and trace the entire graph, the idea behind a continuous graph is I never have to lift my pencil. So the second one has a hole in it, and I have to lift my pencil over the hole. Yep, that is what we call a hole. Okay? So the continuous graph of the three, if we label these number 1, 2, and 3, the continuous graph is number 1. And it is continuous because there are no holes. This one isn't a hole. What do I have right here? A gap, yes. Do we know what we call that gap? It is a space. Notice that the right side is going up towards this blue line but never touching it, and the left side is going down towards that blue line but never touching it. It's called an asymptote. So we could either have holes or asymptotes. So a continuous function, a continuous graph, has no holes or asymptotes. Okay, so number 1 would be the continuous graph. That means that number 2 and number 3 are what we call discontinuous. So number 2 is discontinuous because of that hole. And number 3, quiet please. Cameron. Number 3 is discontinuous because of that vertical asymptote. Now, if you look at number 2, if I wanted to simplify this expression more, what could I do? What could I do? I could cancel the x plus 2. So, when you get a situation where you have a factor on the bottom and a factor on the top that cancel, that is what causes a hole. So, you get the hole when you have a factor on top and bottom that cancel. And where does this hole happen? At x equals what? -2. It happens at the point, the x value that makes the denominator equal 0. So when we've been doing those domain restrictions, x cannot equal 2, x cannot equal 1, those domain restrictions are causing either a hole or an asymptote. Okay? So the hole will happen. To find out where the hole occurs, you would take the denominator and set it equal to 0. We would say x plus 2 equals 0. We would solve that. We would get x equals -2. That's where the hole is. So you take the denominator and set it equal to 0 to find out where the whole is. And that would be on the factor that cancels. All right. Do I have a factor that cancels on number 3? Can I do any canceling here? I cannot. So, when you have a factor on the bottom that does not cancel with the top, that's what causes a vertical asymptote. When you have a factor on the bottom that does not cancel with the top. And then to find where the vertical asymptote is, again, you set the denominator equal to 0. And in this case, it was x minus 2. Solve for x. And we have a vertical asymptote at x equals 2. Now, there are some rational expressions that may have both a whole and a vertical asymptote. You would have to identify which one is a whole and which is a vertical asymptote. The whole comes from the factors that cancel, top and bottom. The vertical asymptote comes from the factor on the bottom that does not. All right, so we have questions on any of those. So one last thing, just getting terminology down. Whole and vertical asymptotes are called points of discontinuity. They're the places where there is a hole or a gap in the graph. The holes and vertical asymptotes are called points of discontinuity. So in your homework tonight, you'll be given a rational expression. Always factor first. See if any factors cancel on the top and the bottom to make a whole, or see if you have any factors on the bottom that do not cancel to make a vertical asymptote. All right, are we okay here? Okay, shall I move on or hold up? Okay, we'll move on. All right. So, we covered basically most of these vocabulary terms. A rational function, you don't need to write these down. I'll tell you which one you do need to write, because we haven't covered it yet. A rational function is just when we have p of x over q of x, and p and q are both polynomials. Continuous graph we talked about. What's the easy way to tell if it's continuous? You don't have to lift your pencil. Trace the graph, you don't have to lift your pencil. Discontinuous, when you do trace it, you have to lift your pencil for a whole or an asymptote. The two types of points of discontinuity are what? Whole and vertical asymptote. All right, what we have not talked about yet are these two. These are just other ways of saying the same thing. When you see a removable discontinuity, what that means is if I could change one point to make the graph continuous, it's called a removable discontinuity. So which type would be removable? A whole. So removable discontinuities are wholes. And it's removable because if I fix that one point, then the graph would be continuous. And non-removable would be what? The vertical asymptote. They'll ask the questions in the homework in different ways using different terms, so you just need to be familiar with what each of these terms mean. Okay, discontinuity. What are the domain and points of discontinuity of each rational function? Are the points of discontinuity removable or non-removable? And what are the x and y intercepts? So this has got a bunch of different things in it. We're going to break it down and do each one separately. The first thing it asks about is the domain and the points of discontinuity. So, with every rational expression, what's the first thing we want to do? Factor first. Ooh, right. Whoa. Okay, sorry. Is there a number? Oh, I think it is. Okay, that is factor first. Okay, I'm trying on my side. All right, so when we factor first, quiet please, we get y equals, nothing we can do on top, x plus 3. What does the bottom factor to? X minus 3, x minus 1? That looks right to me. That would add to -4 and multiply positive 3. Really good. So the first thing it asks for is the domain. Well, we've been doing that from the previous section. X equals all real numbers such that x does not equal what? 3 and 1. Should I also include -3? Nope, we only use the denominator to find domain restriction. So there's domain, that's done. All right, and then it says find any points of discontinuity. Well, when you find your domain restrictions, those are your points of discontinuity. So your points of discontinuity are x equals 3. Sorry, this should be up here, should be a not equal. Domain is x equals all real numbers such that x cannot equal 3 or 1. When you ask for points of discontinuity, that's when we say they happen at x equals 3 and at x equals 1. The third thing it asks for, let's see, are the points of discontinuity removable or non-removable? So let's list the two of them, x equals 3 and x equals 1. Removable means it's a whole, and non-removable means it would be a vertical asymptote. So, do either of the factors on the bottom cancel with top? No. So, they are both what? Non-removable. And what do we call those? Another term for that is what? Vertical asymptote. Make sure you have the V on that. We'll also talk about horizontal asymptote. So both of them cause vertical asymptote. Okay. And then finally it says, what are the x and y intercepts? So this is a review. X-intercept and y-intercept. How we find an x-intercept? Good. We set y equal to 0. And when you do that, we would have 0 equals x plus 3 over x minus 3 times x minus 1. And we want to solve for x. So the first thing we would do is clear the fraction. We would multiply top and bottom, sorry, left and right by the entire bottom. And what happens when we do that? X minus 3 times x minus 1 times 0 over here. And over here, so what happens? These cancel completely. And what do I get on the left? Anything times 0 is 0. So the trick for the x-intercept when you have a rational expression is that you really only have to set the numerator equal to 0. So you don't have to go through that whole process every time. You can just simply set the top equal to 0 and solve for x. So x equals what? -3. X-intercept is where the graph touches the x-axis. So that's just giving us a point on our graph. It goes to the point -3, 0. All right. Y-intercept. Well, for the x-intercept, we set y equal to 0. The y-intercept, we set x equal to 0. So that means in our original equation, we put 0 in for each of the x. So we would have y equals 0 plus 3 over 0 minus 3 times 0 minus 1. On top, we get 3, and on the bottom, we get what? -3 times -1 is +3. So we have 3 over 3, which is what? So the y-intercept is 1. So that means we have the point 0, 1 on our graph. And over here at the x-intercept, we ended up with the point -3. The reason we're reviewing x and y-intercepts is because we're going to be graphing these things. It's nice to have those points so that we can shoot our graph through them. All right. Any questions on domain, point of discontinuity, removable or non-removable, and x and y intercept? Okay. All right. Okay. So we want to do the same thing with this one. We want to find domain. We want to find points of discontinuity. We want to find out if they're removable or non-removable. And then we need to find x-intercept and y-intercept. So we factor first. Can't do anything with the top. Can we do anything with the bottom? Careful, plus instead of minus. That does not factor. So there is no factoring that helps us here. Cannot factor anything. X minus 5 over x squared plus 1. All right, so now let's go through these. The domain. Well, to figure out the domain, you set the denominator equal to 0 and solve. So we would set x squared plus 1 equal to 0. When we subtract 1 from each side, we get x squared equals -1. Well, what does that mean? X equals plus or minus I. That means there are no real numbers that make the denominator equal 0. So that means the domain is x equals all real numbers. No restriction. So there's no number I can plug in on the bottom to make it go to 0. Well, when we see a domain that is all real numbers, no restrictions, that means there are no holes, no vertical asymptotes. So what kind of graph do we have? We have a continuous graph. All right, so points of discontinuity? None. Are those discontinuities removable or non-removable? Not applicable because we don't have any. Okay, x-intercept, what do I do?
Numerator.
Good. Set the numerator equal to 0. So x-intercept is x equals 5. is equal to 0. So we would have y equals 0 minus 5 over 0 squared plus 1. And we would get what? Negative 5. So this means our x-intercept is the point 5, 0, and the y-intercept is what point? 0, negative 5. So now what we're going to do is put all this information together and see if we can come up with a graph or an equation. Any questions on this? All right. So there's one last thing we need to find to be able to do our graph. Let's copy that one. And that is if the graph has any horizontal asymptotes. So we talked about vertical asymptotes, and you saw what those look like on the first graph. So if I have a horizontal asymptote, we're talking about something that looks like this. So right here at x equals 0, I have a vertical asymptote because both the right side is going up towards that red and the left side is going down. So I have a vertical asymptote at x equals 0. But I also have this horizontal line here. Notice as we go out to the right, the graph will go towards this line and not touch it. And as I go out towards the left, the graph will go towards that line and not touch it. That's called a horizontal asymptote. And that's a horizontal line, so it's not x equals, it is y equals. And that line, I said that was x equals, or sorry, y equals 1. So the horizontal asymptote would be y equals 1. So the way that we find horizontal asymptotes is we want to see what this function is doing when x gets really, really big in the positive and when x gets really, really big in the negative. Your y values would then be approaching some number, which is our horizontal asymptote. So there are 3 rules we use for horizontal asymptotes. These are very important. You'll use them forever in every math class from here on out. 3 rules for horizontal asymptotes. For rational expression. So first, if we have the higher power on the bottom, so something like x squared over x cubed plus 3x minus 5. So the higher degree is on the bottom, the higher power. Here's a 3, here's a 2. What that means is when x gets really, really big, the bottom of this fraction is growing much faster than the top. Because when we take a gigantic number and we cube it, it's much bigger than a gigantic number squared. So the higher power is on the top, on the bottom. Bottom's growing faster. That's like having 1 over 1 million. And 1 over 1 million is very close to what? 0. So when the higher power is on the bottom, your horizontal asymptote will be at y equals 0. All right, well the second condition, second situation would be higher power on the top. So that would be something like y equals x to the 5th plus 2x plus 3 all over x squared plus 3x plus 9. our higher power on the top. X to the fifth on the top, X to the second on the bottom. If that's the case, which is growing faster, the top or the bottom? Top. So if we have a gigantic number to the fifth on the top, the bottom cannot grow at the equal rate, can't keep up, so the top is getting bigger much faster. That means this would go to infinity, and that would mean that there is no horizontal asymptote. Not approaching any number. So if the higher power is on the top, we have no horizontal asymptote. So we have higher power on the bottom, higher power on the top. The last situation is if you have the same power top and bottom. So that would be something like y equals 2x to the fourth plus 3x squared over 5x to the fourth plus 2x minus 7. Same power on top and bottom. So that means they're actually, this x to the fourth is growing at the same rate as this x to the fourth. The only difference is the number that's in front of those powers. So the horizontal asymptote would be y equals the ratio of the coefficients of the highest power. Which in this case would be what? 2 over 5, exactly. So the horizontal asymptote would be at y equals 2/5. That's the 2/5. All right, so in tonight's homework, more than most other homework, this video will be very helpful because it's a lot of information. Okay, so I'll post this after this class. Please go to the video to remind yourself. You have to note, but go to the video to remind yourself what exactly we were talking about. So the homework for tonight is on the assignment sheet, which maybe I can do that. Here. The assignment sheet is up to date with our weird schedule. So we are here on 4.3. We're doing 8.3 graphing rational functions. It's page 521. Sorry. Page 521, 13 through 29 odd. We're going to change that to just leave off 29. 29 is the one where you actually graph it. And we haven't put all the information together yet to actually do the graph by ourselves. So it's 13 through 27 odd. Yes. Tomorrow. Yes. Make sure that's true. Yeah, it's not tomorrow. 4, 5, 6, 7. All right. So I will post this as soon as we're done with class.